All right. Okay, so yesterday, of course, as you know, we finished up section 1C, and we ended up with a very complex, very important technique called the method of substitution for integration. So the next section, 1D, introduces us to integrals for exponential and logarithmic functions, and we will start doing that tonight. But what I thought it might make sense to do is take a step sideways and basically get some more practice with the method of substitution, because it can be extremely tricky. We're being thrown a lot of different cases our way, and not everyone is treated in exactly the same way. So it's a kind of technique that really requires quite a bit of practice to get the hang of it. So just to be on the safe side, I think we should take a look at some more examples. Then we can carry on with section 1D, where we can go and look at the integrals for exponential and logarithmic functions. So I put together a short list of problems that we can work on. And of course, I will post the solutions when we're done. So now we come across this first one. Now, it does not appear to follow along with any of the standard trig formulas that we see in the back of our textbook. In fact, why don't we open that up and go find that page where it has a list of all the trig functions. Trig functions, integral functions. Some of them are trigs. And let's see. Actually, I'll tell you what, let's go back to the table of contents. That might be easier. It's a huge book, and sometimes searching through it is a little tricky. For God's sake. Okay. Yeah, this is all right. I'll do it myself. Table of integrals. That's what I was looking for. Okay. So in other words, there's a lot of formulas here that we could potentially encounter, especially down here. You see some of these involve square roots. And so when we see a case like this, it's possible that that's what we're looking for. It may be one of these special cases. But if not, one way we can potentially solve this problem is with the method of substitution. Now, of course, we're going to, in chapter 3, we're going to learn a lot more methods of integration, some very powerful techniques. And sometimes the big challenge is deciding which one is the appropriate one for the case that you're looking at. And that it's been a bit of an art trying to figure out which technique really makes the most sense for the particular problem that you're working with. So here we're going to try to focus on the ones where the method of substitution would be the quickest way of doing this. Often what ends up happening is we have a product of some kind, or possibly a ratio, where one of the terms has a higher exponent than the other one. Well, that could cover a lot of cases, but sometimes it's not quite as straightforward as it sounds. So like this one, it looks not too bad, but it is a little bit tricky. So what we're going to do with this one is we have to decide whether we should let u equal x, or maybe it should equal radical x plus 1, or maybe it could equal x plus 1. So the challenge is to make sure you are able to take the derivative with respect to x and see if the problem can be simplified into the form u du, or something along those lines, something related to this. In other words, something like this, except possibly u has an exponent, or maybe there's a constant in there. We don't have that here. In other words, this first one can't be right, because we need to do something about this x. Sorry, we need to do something about this square root. Okay, so this one doesn't look promising. Now this one is going to be a bit of a mess. because what we're going to end up with here is 1/2 x plus 1 to the minus 1/2 power. And we certainly don't have that in our formula, so we can kind of skip over that one. Now, this is the interesting one. If we let u equal x plus 1, du dx is just 1, so that du equals dx. So you might say, well, that doesn't look right either. Well, let's see. If we use this, what that means is the x, what do we do about the x? Well, if u equals x plus 1, that implies that u minus 1 equals x. So we can replace the x rather, with u minus 1. Here we would have the square root of u, and then this would simply be du. Now, it looks, again, like maybe we're creating a bigger mess than what we started out with, but why don't we take a look and see what this is actually equal to? This one we can multiply it out. By the way, I'm going to write this as u minus 1 times u to the 1/2 power. Now, of course, I can multiply this by both of these terms. U times u to the 1/2 power equals u to the 1 plus 1/2, or the 3/2 power. And then here we have minus u to the 1/2 power, and all of this is multiplied by d. So right now, this looks like it's very manageable. And it is, because these will enable us to simply apply the so-called power rule. Okay, so now this first one will be u to the 5/2 over 5/2 minus u to the 3/2 over 3/2. And don't forget about the constant, because this is an indefinite integral. And of course, we want to simplify these. This first one, for example, dividing by 5/2 is the same thing as multiplying by 2/5. And similarly here, we have 2/3 times u to the 3/2 plus c. And now we can go back and find how we defined u in the first place. We defined u to be x plus 1. And we're done. So that one was kind of a catastrophe, or it appeared to be a catastrophe at first. So sometimes you might have to try different possibilities with these cases. And, as is often the case, I guess we can go look at Symbolab and see if it agrees with us. So yeah, Symbolab has integration. It's not as easy to find what you need in Symbolab. What you have to do is look up here and see if there's one that probably has the functions you need. For our purposes, we can typically go directly to calculus, but we might need other things in here too. So once you get into calculus, you can see it has the integral sign here. So we're going to go back to the beginning, and we have x radical x plus 1. Now, of course, we have to be careful too with Symbolab. Often it can produce a result which turns out to be the same one that we have, but it may be algebraically rearranged somehow. So we should not jump to conclusions. All right, so what is it? 2/5 x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3. Yeah, that's it. We got it. But what a mess. All right. Now, as I mentioned before, they've completely changed this interface to Symbol Lab just since the spring semester. Now, it just so happens that I decided it was worth my while to pay for the premium version of Symbol Lab. So that's what you're seeing here. So I don't know how much of this is going to show up on your screen if you have the free version. But if you notice here, they do have the offer you the option of seeing what they did to get to this point. And so, yes, they're agreeing that we should definitely use u substitution. And they're showing us that we should let u be x plus 1. And you can see, and they're really being very helpful here. Like I said, I can't be sure, then you substitute back. I can't be sure if you have access to this or not, because like I said, I do have the premium version, and you certainly probably don't. But in the past, they did used to have the steps for each problem, or at least in many cases. So just check it out and see what you can come up with. It might be a good way for you to back or double check your work, or give you some hints as to what you're supposed to do next. Now, you can lean on Symbol Lab to do your assignments if you need to, but you're obviously not going to have access to this during the test. So, but I think it's a very helpful tool, especially if you're just simply not sure what to do. It's always nice to know that there's this tool available that can give you some guidance as to what exactly should be done in these types of problems. So, you should not lean on it too much. In other words, don't use it as a substitute for thinking, but you can certainly use it to double check what you've done. All right. So now, not all of them are going to be this messy, by the way. We just happen to start with a tough one. A lot of these are very, very straightforward. Like this next one should be a little bit easier to deal with. So once again, we have a square root. But the reason why this one is simpler is because if you notice, the exponent inside the square root is higher than it is for this term out here. So we can try, for example, 4x squared plus 9. And that means that du is 8x dx. Now, do we have 8x dx? We do not. But remember, we saw some cases yesterday where if we're only missing a constant for something like this, let me rewrite it slightly differently. We need 8x. We don't have it. So what we're going to do is essentially supply it ourselves by doing the following. I'm multiplying on the outside by an eighth, and the interior I'm multiplying by 8. So clearly I have not changed anything. But what I've done is written this in a more convenient form, because if you notice, all of a sudden, look what we have. Radical u du, or u to the 1/2 du. Now we're getting somewhere, because we can use the power rule, 1/2 u to the, actually, let me write it like this. Okay. Now, remember, this is the equivalent of 2/3 times u to the 3/2. And then we have 2/6 u to the 3/2 plus c, which of course is the same thing as 1/3. And now we just have to remind ourselves how we define u in the start, the beginning of the problem. 4x squared plus 9. And there it is. Okay. Oh, now these look pretty scary. Let's see. Let's take a look at our integral table, just in case one of these shows up here. No, it doesn't look like it. It superficially resembles these last three, but no, not close enough. Okay. Because we have this x in the numerator. So, all right, here's what we'll do. Let's try u is 4x squared plus 9. Okay, so what we have here is something that first let's rewrite it a little bit. Now, because this is in the denominator, that's actually 4x squared plus 9 to the negative 1/2 power, and then we have x dx. But we need 8x dx. So therefore, we'll supply it ourselves. So this time, in a similar way to the other one, what we can do now is rewrite this as u to the minus 1/2 du. And using the power rule, what will we get? So we ultimately end up with 1/4 u to the 1/2 plus c. And of course, u once again was defined as 4x squared plus 9. And if you prefer, you can rewrite this as this. Okay. So that one's done. Ooh, okay. All right. Well, you know what? This one looks similar to that last one. Very similar, as a matter of fact. Let's try u equals 4x squared plus 9. So we've seen this again. The only thing that's different here is that this is the same thing as 4x squared plus 9 to the minus 2 power. And again, we need to supply that 8. So this time we have 1/8 u to the minus 2 du. And again, using the power rule, we'll have this, or we can simply rewrite it as, well, since it's u to the minus 1, if we want, we could write it as 1/8u plus c. That's a possibility. We don't have to. And again, so u is defined as 4x squared plus 9. And there you go. All right. Let's see what else we have here. Now, this one is actually far more straightforward because all we have to do is this. You've got x plus 1 to the fourth. Let's just let u be x plus 1. Yeah, you can see this one will be very straightforward. Whenever we have a polynomial like this, it's usually going to work very easily. You just have u to the fourth du. You'll just have x plus 1 to the fifth over 5 plus c. Wow, boy, that was a breeze compared to some of these other ones. Okay. Now, this next one, it also looks like a very straightforward one. We'll let u be 3x minus 2. Okay, so again, we don't actually have that. We need to provide that 3 for the dx. So I'll do exactly that. I'll put 1/3 out here. And here I'll have 3 dx. So we haven't changed anything. And then we can write this as 1/3 u to the minus 11th du. So when you add 1, by the way, remember how this works. So when you add 1 to negative 11, you get negative 10. And then since u was defined as 3x minus 2, we can rewrite it as this. All right. So I'm hoping that we're starting to get the hang of this. And we'll get plenty more practice opportunities, don't worry. Now it gets more interesting. So this time, now it's, I just realized there's a mistake here. This should have been dt. Sorry about that. Okay. Yes, I mean, the variables have to be consistent with each other. So let's try letting u be 1 minus t squared. This time is du dt minus 2t to the du. It's minus 2t dt. And again, we're going to need to supply that constant. So we'll first rewrite this very quickly. I'll put minus a half here. So that we don't change the value of our expression. But what we have done is rewritten it. Oh, wait a minute. I almost forgot there's a 10th power there. Well, that was bad. That would have been bad. Yes, it's to the 10th power. I rewrote it here and I left out the exponent of 10. Sorry. Now we're good. So we're going to have u to the 10th du And then, of course, u is 1 minus t squared. All right. Now, number 8 is going to be very similar. Whoops. Let's try u equals 7x minus 11 du dx. So where does that leave us? Now, once again, we do not have 7 dx in there. So here's what we'll do. Okay, so again, by having 1/7 on the outside and 7 on the interior, we're not going to change the value of our expression. And what we do have is a more convenient form, because now what we have is, very good. Let me just clean that up a little. And then we just remember that u was defined as 7x minus 11. And that's it. Now, here's where it gets interesting. All of a sudden, we've got these trig functions. So what we have to do is quickly remind ourselves that the derivative of sine x is the cosine of x. The derivative of the cosine of x is negative sine x. With that in place, we might be able to, in this case, we should be able to use the u substitution method. So here's what we'll do. Let's try u equals cosine theta du d theta is negative sine theta. And therefore, du is negative sine theta d theta. So now let me just copy this down here. So what we've actually got here then is u cubed. We don't have the negative. So let me write it like this. I almost overlooked that part. All right, so we're going to rewrite this as negative integral cosine cubed theta, and then we'll call this negative sine theta d theta. Oh, yeah, I see that this should have been d theta. Sorry, I'll fix those. Anyway, so now what we actually have here is negative u cubed du. So it looked like a nightmare at first, but that's all you have to do. It's very similar to what we were already doing. So remember, the u was defined as the cosine And that's it, we're done. All right, and then this one, yes, I see that now. When I typed these up too quickly, I guess. So this one will be a lot like the one we just did, except this time, now keep in mind, the sine has the higher exponent. So let's try to let u be sine this time. Usually that's the way to go. Whichever term has the highest exponent usually is the best choice for you. Oh, and I did it again here. It's just such a hard habit to break, dx. It's d theta this time. All right, do we have that? Actually, this time we do. We don't have to make any real changes. So basically, I can even just write it like this is just equal to u to the 7th du. You're going to end up with sine 8 theta. Okay, very good. Beautiful. All right. Now, oh, by the way, one more thing. Now, this is something that's always driven me crazy about Microsoft Word. The default mode in Microsoft Word is no page numbers. So I'm going to insert that one right now. I don't understand what they're thinking. You'd think it would be the other way around. How is it not helping us to have page numbers? I mean, sometimes they make some unbelievably dumb choices. But anyway, so this way, if you want to print this thing out, and you drop the pages on the floor, at least you'll know which page is which. So, all right, let me save this. And I'll post this on Moodle so you can go through it again. And if you want to, you can go take these into Symbol Lab, and we'll also show you what what you're supposed to do. That will come in especially handy when you start getting towards the end of a couple of chapters where you have a bunch of problems and you're not absolutely positive what technique you're supposed to use. Sometimes it can take a lot of cleverness to use these techniques or figure out which is the right one. Okay, actually, let me do this. And as always, I'll save it as a PDF file because if you're using the Mac, this might not look normal on your computer. There's a very real chance that it'll get garbled somehow, or it won't look quite right. Oh, one more thing too. If you notice, the handwriting is great as far as it goes, but it really, really greatly increases the storage requirements. So this is actually a pretty large document right now. So we don't have to watch it. Let's go back and open up chapter 1D, where we're going to focus here on exponential and logarithmic functions. Now, these are actually very straightforward. For example, the integral of e to the x, dx is simply e to the x plus c. And this is a more general case. Any constant raised to the x power, the integral is a to the x over log a plus c. And the reason why we say that this is a special case is because if I replace this x with an e, the a with an e, Oh, okay. It's trying to let me know that it's done. Okay, great. I always like to double check. Sometimes you can accidentally make a mess out of this. Yeah, it looks pretty good. If you get your stylus in the wrong spot, you can accidentally drag things around and you can really make a mess. So it looks good. Okay. Anyway, so if A equals E, the key to the whole thing here is that log E is equal to 1. So in other words, in general, the log of any base of the base is 1. For example, the log base 10 of 10 would just be 1. So we'll review these properties as we go along. Now here, for example, it's e to the minus x. You might say, wow, what do we do now? So here's what we're going to do. When you have e to the x, we're going to use the method of substitution, but maybe in a way that maybe you weren't expecting. Let's choose u to be just the exponent, not e to the minus x, but just the minus x. Now, the reason why you know that this is going to work is because remember what we're trying to do. We have to make sure that everything else in this expression is either, in this case, dx, or at most, it's different by a constant. So what we need to do here is supply that negative so that we can write this now as minus e to the u du. Okay, so we end up with just minus e to the minus x d plus c. Now, how about this one? Actually, let me leave this there for another minute. In fact, I'll tell you what, I want to neaten it up a little bit. There it is. Okay. Oh, by the way, I think you probably noticed by now that every time I write on these slides, I always post the original version of the slides plus the version that I've written on. So you can go back and look at these if you want to. You can tell them which one is which because they have dates on them. In the title, I mean. All right, how about this one? So you probably already have a sense of what you're supposed to do here. Instead of letting u be e to the minus 2x cubed, let's just try minus 2x cubed. So we don't exactly have that. We're only missing the constant. So you've noticed by rewriting it like this, we're missing the negative 6. So now we actually have minus 1/6 e to the u. Oh, no, it's here. Sorry. E to the u du. Okay. Now this one looks like it's going to be a disaster. Oh, let me just leave it there for a minute. So the next one we're about to see is kind of a mess, but we'll work with it. So, all right, let's see what this one is all about. Ooh. Okay. So as is often the case, probably the best bet is to look for the messiest part of the expression. Why don't we try 1 plus e to the x, not the entire square root. Let's just leave it and let's see what happens. Now, there's no guarantee that this is right, but ah, I think we have a winner here. So first we'll rewrite it in a more convenient format. Okay. So what we actually have here then is radical u du, or u to the 1/2 du. Oh, sorry, I wrote the wrong thing. Sorry, this is u. And then we replace u with 1 plus e to the x plus c. So yeah, it started out looking very terrifying, but it turned out not to be. And of course, if we chose the wrong u, we would have discovered it pretty quickly, because we would have noticed that we ended up with an expression that was even messier than what we started out with. Okay. Ooh, this next one looks pretty scary. Oh my God, what do we do? All right, so again, because this is the messiest part of the expression, why don't we just let u be 3e to the x minus 2 du dx is 3e to the x, and du equals 3e to the x dx. Oops. And so we'll rewrite it slightly. And you'll see that we're missing the 3, so we'll supply it ourselves. So we got 1/3 the integral of u squared du. And so let's move this to the next slide. And remember, u is equal to 3e to the x minus 2 cubed and divided by 9. Okay. Now, the next one coming up is a definite integral. Now, of course, the techniques we're using here do not depend on whether this is a definite or indefinite integral. It works the same way. The only difference, of course, is that with the definite integral, we're looking for a specific constant. The actual technique for finding the integral, it does not change. All right, so what's next? Now, as we've seen before with these exponential functions, it often pays to let u be simply the exponent of e. Let's try that. So actually, this is -1. So du is negative dx. We don't have a negative dx, but what we can do is rewrite this slightly. So we end up with minus e to the u du. Now, this is minus e to the u. Now, since this is a definite integral, there's no constant. It has to be evaluated between 1 and 2. And of course, before we do that, we have to replace this u with its definition. So what does this give us? Okay, so what I've done is, of course, here in the first term, I've replaced the x with 2. Then I subtract the term evaluated when x equals 1. Let's move this to the next slide. Okay, there we go. And if you want, you can rewrite this as -1 over e plus 1. Because e to the -1, of course, is 1 over e. So, all right, what's next? Here's another good one. Let's try u equals 2x. So we don't quite have that, but we can certainly supply that missing 2. We have dx, but not 2 dx. Let's multiply by 1/2 and by 2. So we end up with 1/2 e to the u du. Perfect. Actually, there's a lot of ways we can express this. The books that I've seen usually use the square brackets to indicate that we're going to evaluate this. In this case, from 0 to 2. Okay. All right, so we end up with 1/2 e to the 2x valued from 0 to 2. So I'm replacing the x with 2 here and the 0 here. I subtract one from the other. So I guess we could just leave it like that. All right, so now we're going to look at an interesting application of this. It's time we looked at a physical example. So you might recall from high school biology that bacteria grow at what's called an exponential rate. And so what that means then is that an exponential function has a very interesting behavior. This will be, well, even that doesn't really show you how quickly it grows. This could be, for example, y equals e to the second power or something like that. Actually, I'll tell you what, let's go to Symbol Lab so we can get a better look at this. Oh, wait a minute. Sorry, I didn't. It's not 2, it's 2x. Sorry about that. E to the 2 is a constant. I wrote it incorrectly. Sorry about that. It's 2. What am I doing? Yeah, you can see, you get the point. It's going up very quickly, very, very quickly, and it'll actually continue to get steeper as we go along. Now, for many physical applications where we can't have negative numbers, so we really only focus our attention on the first quadrant. Okay, so this would be the only part that's actually relevant. But the idea here is that it's a very rapid growth rate, and bacteria have been observed to grow at an exponential rate, which means it's first their population grows fairly slowly, and then before you know it, it's growing like crazy. So why don't we assume that the growth rate for bacteria is described as Q of t equals 3 to the t power. Now, Q means quantity, t means time. So this is meant to be the quantity that we observe at time t. So the graph of that, 3 to the t, let's go back here and look at it. I'll tell you, here I'll just call it 3 to the x. I think, actually, I don't think Symbol Lab cares what we call it. Let's try, just to make sure, Q equals 3 to the t power. In fact, it won't even care if I try to use this functional notation. I don't think that'll confuse it. Yeah, exactly. It grows very slowly, and all of a sudden it just grows like crazy. It cuts through the horizontal axis at 0, a vertical axis at 0, 1, and then it just goes to the roof. So now it turns out that if I want to know how many bacteria I have at any given time, what I'm actually doing is integrating it. Okay. So in other words, if I want to know how much bacteria I have at any time, what I'm going to do is just take the integral of that function. And then I can substitute t and find out what what the function looks like. Now, for this one, we're going to need to go back, revisit this rule right here, because our function is a constant. And the key here is that the exponent is the variable. This is what uniquely characterizes an exponential function. The variable is an exponent. That's what really makes it different from the others. X, or whatever the variable happens to be, is actually the exponent. With all the other functions we've looked up to this point, that was never the case. But here, the variable is actually an exponent. So what this is telling us is that based on this rule, this is the formula that we'll need to calculate the amount of bacteria at any given point in time. So we're being told also that we start with 10,000 bacteria. Okay, we're not starting with 0. We're assuming that there's already a bacteria colony that starts with 10,000 bacteria, and we'd like to know how many there are, let's say 5 minutes later, or whatever, 5 hours. So 5 would therefore be substituted in here as time. And it's interpreted as a certain length of time in the future. T equals 0 means now. Any other t means some point in the future. So in this case, Q of 0 is the starting value. Q of t means how much bacteria is there at any point at that far in the future. So in our case, oh, by the way, I've got 10 here instead of 10,000. We're assuming that this is in thousands. T is 0 for today. So what that means then is that since our integral is 3t, Q of 0 actually, let me write it out directly, 3t dt. So in other words, by telling us that Q of 0 is 10, that enables us to solve for the constant. Okay, this implies okay, so oops, no, sorry, I did this wrong. N is 3 to the 0 over log 3 plus c. And therefore, 10 equals 1 over log 3 plus c, which implies that c is equal to 10 minus 1 over log 3. So now, after 2 hours, so remember, our final result was the integral was 3 to the t over log 3 plus the constant. But since our constant is 10 minus 1 over log 3, this is now how we're going to figure out how much bacteria we have at any point in the future. After 2 hours, all the t's are replaced with 2. And whatever this number is equal to is our answer. Now, I can see on the next slide that that's approximately equal to 17.282. But since this is in thousands, that's equal to 17,282. So basically what just happened here is that we started with Our intercept is the starting point. So the vertical intercept was this 10 minus 1 over log 3. After 2 hours, we have 17,282 is the amount of bacteria. Now, by the way, 10 minus 1 over log 3 is equal to, hold on one second, 9.0. Well, actually, no, that's not right. They told us that we started at 10. Sorry, what am I doing? This is just 10. All right. So no, forget this part. We started at 10. And we end up 2 hours later at 17,282. Okay, so that's what we know. We know where we started, we know what the growth rate is, and therefore we can predict the value at any point in the future with this formula right here. Okay. But yes, so in other words, in order to illustrate this, we need some variable that grows at an exponential rate. Now, later on, we're going to see an example with interest rates. I'm sure, I mean, the bacteria are interesting, but the interest rates are something you might run into in your daily life. So later on, one of the examples of these functions will take the form of an interest rate example where under certain conditions, interest rates can also grow at an exponential rate. And if they do, that means you could figure out very quickly and easily how much money you'll have in the bank at any point in the future, given how much you started today and with today and how much time is involved. All right, now here's one that looks really tricky. Oh my God. What do we do now? All right, well, I'll tell you what, let's do this. Let's rewrite it slightly. One over x is minus, x to the minus 1. Now, 1 over x squared is x to the minus 2 power. So here's what I'm going to do. So by writing it like this, oh, no, I did. What did I do? Sorry. This is x to the minus 1. I was just sloppy there. Sorry. It's x to the minus 2. And this is e to the x to the minus 1 power. By writing it like this, it should be a little bit easier to see that u should be the exponent here. So that du is minus x to the minus 2 dx. So do we have that? Almost. We need the negative. So I've supplied the negatives, rewrote it slightly. So you can see that we actually do have e to the u du. Oh, that worked out rather well. So we have Okay, so let's substitute. So for this, I tell you what, it might be a little bit easier to rewrite this as 1 over x. Oh, what did I do? No, sorry. Not square root of x, square root of e. I think that's a little bit cleaner than leaving it x to the minus 1 power. Ooh, that was a mess. But it's like I said, some of these techniques really require a lot of practice. But at some point, you start to get good at it. But there's certain patterns we wanted to see. For example, here, every time we did one of these with e to the x, we always chose the exponent of e as our u. And that worked great for these. That doesn't prove it'll always work, but I think it's probably a good starting point in making sure that you're heading in the right direction. So anyway, I guess our time is up. We'll stop here and we'll continue with these examples. And then down later on in the chapter, we'll look at logarithms. And then what comes after this is applications. So like I mentioned before, we'll see some applications. One of them will be interest rates, applications of integrals, that is. And then we'll dive into the more complicated techniques. We're going to have, in chapter 3, several very, very complex techniques that we'll be using to come up with integrals for the very messy cases. And so there's a lot of work involved in doing integrals. So we'll be diving into that very soon. And then we can get back to derivatives, our old friend derivatives, after that, and learn some more applications of them. So anyway, I guess we'll stop it right here, and I'll see you next time.